So continuing on in section 2.4. So to recap, what we had done is previously we had defined a way to represent angles of any size by embedding them inside of the xy axis. And then we translated our right triangle definitions for sine, cosine, and tangent into a new definition. Instead of being based on the side lengths of a right triangle, we're based on the coordinates of a point on the terminal side of our angle that we embedded into the xy axis. We're going to continue kind of on that same discussion, but before we go forward, we're going to do an example of finding, say, cosine of 150 degrees. So what I'm going to do is I'm going to start by drawing my 150 degree angle. So I always draw the initial side of my angle on the positive side of the x-axis. And then I'm going to rotate from that initial side 150 degrees. So 90 degrees to here, and then 60 more puts me somewhere over here. Everybody okay with this idea? I'm now going to draw a vertical from my from the terminal side down to the x-axis. Which makes this right triangle here in green. And I'm going to determine what this angle here is. Who can tell me what this angle is? It's got to be 30 degrees, right? We've done 150, and then if we do 30 more, that's 180 degrees, and that's a flat line. Everybody agree with that? So that also means that this angle has got to be 60. So what I'm looking at here is a 30, 60, 90 triangle. Everybody okay with that? I remember the side lengths of a 30, 60, 90 triangle. The side next to the 30 is the x square root 3. The side opposite the 30 is the x. And the hypotenuse is the 2x. Everybody okay with this? There's a little bit of an update, though, we need to do to this. Notice what part of the x-axis is the x square root of 3 on. It's on the negative side of the x-axis. Does everybody see that? So I need to make this side length negative. Now, I don't really have a negative side length. What I really have is the point P, whose x-coordinate is negative x squared of 3, and whose y-coordinate is positive x, which, when I look at the location of this point P, is obviously what's going on here, right? Can we see that? So I know it seems like kind of counterintuitive to label a side length of a triangle negative, but we're just kind of using that reference triangle there as a visual to connect our ideas of right triangle trig to this new point definition for trigonometry. Michael? I'm talking about this point right here, though, which is negative x squared of 3 over and positive x out. Yep. So again, I used the triangle to kind of connect our old ideas to this new one, But I'm really talking about that point on my terminal side. Everybody okay with that? So now I can use my definitions of cosine. So I can say that cosine is x over r, or since I've drawn this triangle in here, I can say it's still adjacent over hypotenuse. Or just negative square root 3 over 2. Is everybody okay with what we've done there? Okay? So, an interesting question becomes, is when are these sine, cosine, and tangent going to be positive or negative? So let's think about where the terminal side of our angle is going to lie, and that should be able to tell us whether these are going to be positive or negative. So in the first quadrant, any point is going to have a positive x-coordinate and a positive y-coordinate, correct? In the second quadrant, we have a negative x-coordinate, but a positive y-coordinate. In the third quadrant, we have a negative x-coordinate and a negative y-coordinate. And in the fourth quadrant, we have a positive x-coordinate, but a negative y-coordinate. So if we remember our point definitions for sine, cosine, and tangent, we remember that sine is y over r, cosine is x over r, and tangent is y over x. What can I say about the sine of r? Remember, r is the distance from the origin to that point on our terminal side of our angle. R will always be a positive value because r is always a distance. It's not represented by either the x or y coordinate. So r is always a positive value. If I look at this then, in the first quadrant, sine would be positive over positive, cosine would be positive over positive, and tangent would be positive over positive. So all three of them are going to be positive in the first quadrant. It's the distance from the point to the origin. Mm-hmm. Yep. And again, since r is a distance or a length, it's always got to be a positive value. You're welcome. In Quadrant 2, we have the x's are negative, so sine will still be positive over positive. Cosine, though, is going to be negative over positive, so cosine would be negative. And tangent would be positive over negative, which is negative, so tangent would be negative. I'm only going to write down the positive things on our little list here. if I move to the third quadrant, I'd have negative over positive for sine. Cosine would be negative over positive. But tangent would be negative over negative, which is positive. And then if I move to quadrant 4, I have the x's are positive, but the y's are negative. So sine is negative over positive. Cosine is positive over positive. And tangent is negative over positive. So I can remember which function is positive in each quadrant using the acronym all silly turtles crawl. Or you can make up your own acronym there. But it's just an effective way to remember which function is positive in each quadrant. So if you don't like that acronym, you can make up your own. I'm sure that you can come up with something more creative. This is the one that I remember from my high school. It must have worked because I remember it 40 years later. It hasn't been 40 years since I've been in high school. It has been more than 20. Life moves pretty fast sometimes. All right. Does everybody feel okay with this? We haven't done anything too difficult here. We just kind of took our point definition and what we know about the sign of the x and y values in each quadrant and applied that. So what we're going to do is define something called a unit circle. So a unit circle, which I think I mentioned earlier, is just a circle that's centered at the origin and has a radius of 1. If I go back and I look at this previous example here, this triangle that we drew, or this point P that we drew, I guess I should say, isn't necessarily on a unit circle, because if I look, depending on what value I choose for x, the radius would not necessarily be 1, right? What value of x would I have to choose for this to lie in a unit circle? 0.5 or a half, because 2 times a half would give me 1. So what we want to do is we want to create a circle that is going to contain all the points for the angles that we can find the exact values for. So we want the angles that are multiples of 30 degrees, 45 degrees, or 60 degrees. And we want to label those points that correspond to those angles on our unit circle. page, as well as one that's filled in neatly. This is just a blank copy of the unit circle. I think when I looked at this after I printed out the wrong class names on it, because I used it for a previous class. So you can ignore the wrong class label. Okay. So let's go first through and label the angles in degrees, because most of us are more comfortable labeling these in degrees than we would be labeling them in radians. So let's, right here, this would be 0 degrees, right? Or you could write it as what other degree measure? 360, right? Typically we start with 0 though. The next one is 30 degrees, 45 degrees, 60 degrees, 90, 120, 135, 150, 180, 210, 225, 240, 270, oops, I think it's supposed to be on the big one, 270, 300, 315, 330. Okay, so far? What we'll do next is we'll go through now and convert each of these angle measures into radian measures so that we have that labeled on here as well. So 0 degrees is 0 radians, 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3, 90 degrees is pi over 2, 120 is 2 pi over 3, 135 is 3 pi over 4, 540 is 5 pi over 6, 180 is pi, 210 is 7 pi over 6, 225 is 5 pi over 4, 240 is 4 pi over 3, 270 is 3 pi over 2, 300 is 5 pi over 3, 315 is 7 pi over 4, and 330 is 11 pi over 6. Everybody okay with what we've done here? Again, you guys know the conversion factor for translating radians to degrees or vice versa. That's basically all I did there. I just wrote down the answers because the calculation is kind of trivial. Is everybody okay with that? Mark? For 300 is 5 pi over 3. Man, do you guys need some drinks of water or something here? Everybody's so coffee. All right, so now let's fill out the x and y coordinates. So one of the features on the unit circle is that if the radius is 1, the x coordinate is essentially our value for cosine, and our y coordinate is our value for sine, because we remember that cosine, oops, I should probably say theta, not x here, because cosine theta was x over r, but if r is 1, cosine theta is just going to be x. x, right? Similarly, sine theta is just going to be y. Is everybody okay with that reasoning? Okay. So if I look at 0, what is the location of this point? It's 1, 0. Did I actually compute sine or cosine to determine that? No, I just looked at where it lied or lay on the xy axis, right? Okay, let's skip over here to 90 degrees. What is this coordinate? 0, 1. And then at 180, negative 1, 0. And down at 270, thank you. Those those 4 angles have a special name. They're called the quadrantal angles because they are angles whose terminal side lies on the boundary between one quadrant and another. That's not important that you know that, but it's like a little nice aside that they do have a special name. Okay. So, for 30 degrees, if I look at my 30, 60, 90 triangle, we know this. So cosine would be x squared root of 3 over 2, which reduces down to square root 3 over 2. Sine would be x over 2x, which reduces down to 1/2. So any place where I can draw a triangle back to the x-axis that has a 30-degree angle in it is going to have those same values for sine and cosine, with the exception of maybe some negative sign changing. So in the second quadrant, that same location is here. So it's negative square root 3 over 2, but positive 1/2. In the third quadrant, that location is here. In the third quadrant, both are negative. And in the fourth quadrant, that location would be here, where just the y coordinate is negative. Is everybody okay with what I did there? Now let's move on and look at the 60-degree angle. So if I'm looking at cosine of 60 degrees, that is going to be x over 2x, or just 1/2. And sine of 60 degrees is going to be square root 3 over 2. Now I'm going to copy this in at all the places where if I draw a right triangle back to the x-axis, I end up with that 60-degree angle. So, over here, I'm going to have, in the second quadrant, it's this spot. Again, I'm going to make the x negative. In the third quadrant, we're talking about this spot. In the third quadrant, both the x and the y are negative. And in the fourth quadrant, it's this spot. Here the x is positive, but the y is negative. Everyone okay to hear? Okay. Now let's do the 45-degree angle. So again, I recognize if we're talking about 45, we can use our 45, 45, 90 triangle to determine the sine and cosine in these situations. Sine is going to be x over x square root 2. So when we simplify that down, we get square root 2 over 2. And the same thing for cosine, right? I'm now going to copy those into all the locations where I can make a 45-degree angle when I draw that vertical line back to the x-axis. There's only 3 spots left. That's all going to be those spots, so I just need to make sure I draw those in with the appropriate signs. Yes. Square root 2 over 2. That's what you needed? Okay. No problem, dude. I know that this is small and maybe not that neat looking. I promise I have a printed out, like typed in version on PowerSchool that if you want to look at, you can have that there to look at. So, we've done this. Everybody okay here? So again, if we update our point definition with the assumption that we're working on a unit circle where the radius is always 1, our definitions kind of update to here. Everybody okay with that idea? Okay. So let's do some examples. So let's say we wanted to find sine of 120. I recognize that 120 degrees is one of my angles that appear on the unit circle. Specifically, 120 is right here. I know that sine is the y-coordinate from my unit circle at that location. So I can say that sine of 120 is square root 3 over 2. That's it. If I want to do tangent of 5 pi over 4, I recognize that fourths, pi over 4s, are units or are angles on my unit circle. So if I go back to my unit circle and find 5 pi over 4, I see it right here. Tangent, I know, is y over x, so I'm going to take negative square root 2 over negative square root 2 over 2, which does reduce down to just 1. And then c, let's say we want cosecant of 390. Now, 390 is not an angle on my unit circle, but it is coterminal to an angle on my unit circle. So if I do 360 and then 30 more, that's to 390, right? So the angle I really care about is 30 degrees. Everybody's okay with that idea? Cosecant, I know, is 1 over y. The y-coordinate in this case is 1/2. So this is equal to 1 over 1/2, or 2. So what is the unit circle here really? It's just condensing all my information from these angles that we can determine exactly, these multiples of 30, 45, and 60, into one location. Michael? No, I would say that unless I'm telling you that, like, we're doing a quiz on it or something, I would not say you need to memorize it. And I would not say, even if we're taking a quiz on it, you need to memorize it if you can determine, if you can use your special right triangles to fill in the values. I never memorized it. I just knew how to create it and get the values that I need from it. And I think that that's probably a better use of your time than to, like, go crazy and memorize the values. Because I can understand how to get the values really quickly. To memorize all the values, to me, feels really overwhelming. Yes. Yeah, I would provide you a unit circle on, I think, all of your tests. So let's do another example. So let's do this problem. We're asked to find the value of sine theta if we know that cosine of theta is 5 over 7 and that cotangent of theta is negative. So I'm going to start by drawing a picture. So I know that cosine is positive in 2 locations. It's positive in the first quadrant and in the fourth quadrant. Everybody okay with that? How did I do that? All silly turtles crawl. So all first quadrant, cosine, fourth quadrant. Everybody okay with that? So I have 2 possible locations for this angle theta. Which location I want, I'm going to be able to tell by using the cotangent is negative. So in the first quadrant, all sine, cosine, and tangent are positive. If tangent's positive, what do I know about its reciprocal? Also got to be positive, right? Down here, tangent is negative, which implies that cotangent is also negative, right? So I don't care about this triangle. The one I care about is this one down here. So if I do that using cosine, I know that this is 5, the adjacent, and this one is 7, the hypotenuse. And I know that the opposite side is got to be negative because this is some point something, well, I guess it's 5, comma, and then it's got to be a negative value there. Everybody okay with that idea? Okay. And to find that, I'm just going to use the Pythagorean Theorem. So square root of hypotenuse minus the leg, which is the square root of 24. Oops, forgot to write my negative. Which simplifies down to, what is that? 2 square root 6, I think. That's right. Do you guys remember how we simplify radicals like that? So I can think about the square root of 24 as square root 4 times square root 6. and the square root of 4 is just 2, right? I'm just trying to pull out perfect squares, or factor out perfect squares, basically. You guys remember doing that last year? Barely. Right? 24 is just 4 times 6, and 4 is a perfect square, so I can just square root 4. Mm-hmm. Yeah. Yep. Okay. So, again, what I was looking for now is sine theta, which is going to be opposite over hypotenuse. So it's going to be negative 2 square root 6 over 7. Yes? Probably, but not a ton. So, like, if you had instead negative square root 24 over 7, I'd probably just take a half point. So not like an enormous amount, but you should be simplifying the radicals when possible. But it's not like you've given me the wrong answer there. You just didn't do the simplification. You know what I mean? Okay. That is going to close our chapter 2. So that is it for chapter 2. So we do have to finish the last of the homeworks from chapter 2. So I think that is 47 to 60.